Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi friends, so we continue with the class 12 discussions with electronic devices. We've come a long distance here. So before we go any further, let us do a quick rewind and from where we left off last time, right? So last time we were looking at electronic devices, and notably we were looking at the diode, right? And we were looking, so we explained the following, right? A diode is usually represented as a triangle and a line, right? Or triangle and a line, right? The line represents the N type, and the triangle is kind of like the P-type side. Now, when you connect a positive battery to the P-type, you are in forward bias, right? You reverse it, you are in reverse bias. Now, there is a second type of diode that we introduced, which is always connected in reverse bias. So in the forward bias region, you will get a curve like that. The I versus V is somewhat like that, right? It's like that. Now, in a reverse bias, you have a diode working differently. Okay, so what happens in reverse bias, is what we were discussing. So I'm going to quickly go over that, so you kind of get another shot at understanding that. So, okay, so now in reverse bias, the PN junction, like typically, is just shut off. Okay, so if you work below a certain voltage, there is very little current that flows. So that's why when you offer a sine wave, right, one half of the sine wave passes through and produces the current, and the other half is basically shut off. So your output will look something like that. When you pass it through the diode, and you take the voltage across the diode, it will look something like that. Okay, so the second part is cut off, right? So this is the forward bias case. Now, what happens in the reverse bias case? The reverse bias case, the P side is connected to the N side of the battery, right? And if you have AC current like we showed, right, that is AC current, then we are referring to this other side, right? So now the only current that's possible is through the holes, that is the minority charge carriers, right? So they produce a very little current. Okay, now so look at this. So here is the P type, then you have the negative connected to the P type, the positive connected to the N type. This is what is called reverse bias. So what happens in reverse bias? Very little current flows, okay, up until a point, and that point is when suddenly you have everything little bit breaking down, right? So now speed increases, they collide with the valence bonds, and the electron, they collide with the valence electrons, and the bonds get broken. So when the bonds get broken, there is a lot of current all of a sudden, and so that is called avalanche breakdown. Avalanche breakdown occurs in a reverse bias PN junction diode, which is moderately doped and has a thick junction. That means its depletion layer width becomes broader, right? Remember that the depletion layer is very thick when you reverse bias, right? In forward bias, the depletion layer is very thin, right? So in reverse bias, depletion becomes very thick, but still going against that voltage, you push it beyond that, the voltage that it supports, the whole thing collapses, and then you have what is called avalanche breakdown. Avalanche breakdown, I don't know if you, the term avalanche is like when you have snow that drops from a height down onto a cliff, you know. So then when that whole lot of snow falls, it brings with it so much, that is called an avalanche. Okay, so avalanche breakdown usually occurs when we apply a reverse voltage across the diode, you know, obviously higher than the Zener breakdown voltage VZ. Okay, so this is the knee of the avalanche breakdown. So beyond that knee, you have the Zener voltage. You know, this is the Zener voltage, and then you things break down. Now, the Zener diode is you know, is the diode that is operated in reverse bias. Okay, now and so it is used primarily as a switch or as a voltage regulator. So now, what do you mean by as a switch? This is a very important idea as a switch. So now, and we will discuss this more when we discuss the transistor. Now, a transistor is this basically is a two-port device. There is a plus and a minus on a Zener diode. Transistor, on the other hand, is a three-port device. Now, in a Zener, right? So what happens is, you know, under when the voltage increases to a certain level, then the whole thing, you know, it's the voltage that defines when it turns on in a Zener diode. So beyond a certain voltage, it clicks, and there is a lot of current suddenly which starts to come. So typically, the it's a highly doped PN junction versus the very low level of doping in normal junction. So now the depletion layer is thin, right? So now you are using it in a reverse bias condition in a when you charge it the other way, therefore the depletion layer expands. And so the Zener diode has this extra dash there, you know, so they have that line, this line, and that line. Normally, you just have a straight line if it's a normal diode, right? Now that extra dash line tells you that it's a Zener diode, then the breakdown occurs at a later place. Okay? So now, as a voltage regulator, how does it work, right? So you have an unregulated input, right, which where there are two parts. One is the IL, right? And so now, when the voltage suddenly increases, normally this is open. You know, this is an open. There's very little current going through IZ. But when you suddenly have a surge, what happens is this also starts to conduct, and therefore this part is you know, held at a you know, is saved from greater current, right? So you have a resistor here. There is therefore the current that is, right, that is seen here is because this is the short, bulk of the current goes here, very little current goes there. Okay, and as a result, you therefore have this tends to become a short at that higher voltage. Okay, when the Zener comes on, avalanche breakdown occurs, and above that particular voltage, it protects this from the surge of a current, which then can potentially destroy this you know, this particular load, right? So to protect it, they have the Zener, and then all the current goes through it. The other thing that they use is the fuse, right? The fuse will just break, therefore you will not have any power anymore, right? But a surge protector, on the other hand, or a voltage regulator, keeps the voltage regulated in the event of a sudden surge, and it is doesn't switch it off. Things keep continuing, but it is regulated. A regulator is different from a fuse. Okay, so this is the regulator case. The Zener diode starts to conduct, and very rapidly the current increases, and it becomes a short after when the voltage goes beyond a particular value, right? When, you know, when the voltage exceeds a particular value, it starts to conduct and becomes a short. Okay, so that is a typical you know, when it is used you know, as a protector, as a voltage regulator. Now the other setting is this way, right? This is the same as this one. Okay, this is the you know, standard case. You have the power side, and you have the RB, then you have the RL. Okay, 5-volt breakdown, 2 watt power rating, right? So typically most devices, they particularly DC devices, they will have some kind of a regulator, to protect against the surge, because the rectifier, sometimes it's related to the rectifier. The rectifier may just pass things through, pass a high voltage through if there is a AC surge, right? And so a lot of these devices, they are built for to run with DC, like for the laptop, etc., built to run with DC. Therefore, for these devices, the Zener is a particularly useful regulator. So the 5-volt, 2 watt power rating. So when it exceeds that 5 volts, it starts to conduct. At 10 volts. The the IB will be, the VS in this case, right, is equal to 10 minus 5 volts, 5 volts, and then the IB is 5 volts divided by R, right? And so because of that, that sets a bar to the current, right? So and therefore, because this is the current through this, this is completely protected. The voltage across this declines to a very small level, because when at in the knee of the curve, this is almost like a very small resistor. Okay, so you have a very small resistor coupled with a very large load. So then you have a corresponding, most of the current flows this way. The current flowing that way is small. Therefore, there is a protection of the surge. Now, the photodiode is a variant of, it is, it is also works in reverse bias. In reverse bias, current is due to the minority carriers, right? Now, the electron-hole pairs that is generated is directly proportional to the intensity of light. This is knocked out of these minority charge carriers. Okay, now, in a photodiode, light is applied on the diode, and then that produces a current across the diode. So now we will briefly look at the photoelectric effect right after we look at this. But another application of this is what is called the light emitting diode. Today, this is these two, the photodiode and the light emitting diode, are extremely useful tools, and they are, in the age of green energy, light emitting diode is slowly becoming the default choice of light. Okay. Now we also see LED displays, right? LED display also is a similar technology. Okay. Now, and of course, you have the LED light. I have several LED lights in my house. Okay. So now here, the when a current flows through an LED, it generates light. See, it is the opposite of this. Here, light generates a voltage across it, right? Light is the energy that comes. Now, the LED, on the other hand, is when you attach a source, it then emits light. Okay, and here, it is, it follows the, this, it follows this idea of, when is a electron goes from a higher. We looked at those various scattering lines, goes from a higher level to a lower level, it emits a photon, right? So when the electron goes from a higher level to a lower level, it emits a photon. And so that is roughly how the LED works. Now, the other side of it, so LED is a very important technology. You are, of course, I can only spend so much time. So, but please take a look at how LEDs work, because a lot of displays to lighting, they all work in this form. But basically, this is the basic idea. You apply a voltage, and then it leads to a electron going to a higher, and then when it comes down, there is an emission of light. Now, the solar panel, it has a thick P and a thin N. Okay, so when light falls, the PN junction absorbs the photons, and it therefore then emits. It then leads to an electron being pushed out. Okay, so it has a thick P and a thin N. Okay, so the thick P is in the substrate. Okay, then you have the junction between the P and the N. Then you have a very thin N on top. Typically it is, it is few microns at best. And the less they put there, the better. For them. So the whole thing is, of course, very thin. The thinner you make the solar, because the most the costly part is to make that crystalline silicon. And when you have to make such a big version of it, then the less silicon you put, the better it is. So now, when light hits the N part, right, there is a electron flow from the N side, and then there is a whole flow from the P side. So there is the light pushes the electrons in the N type out, right? Because absorbs energy, it floats out. So when it floats out, there are free electrons released, and so that leads to it acting like a cell. Okay, so that is roughly how it works. And so then you have the minority hole carriers, which are also outbound this way, right? And then the electron this way, right? So you have two sets to that. So now, when does this happen? When this happens, when the light exceeds this the voltage, that the field that is that exists between the depletion layer, right? So when that happens, there is the incoming light has an energy which exceeds that base energy. Then you start to see a current that is set up, which then produces a electron hole pair. Okay, and then so when the circuit is complete, the electron returns from the N side to the P side, right? So that's how this works, right? So now you have typically the N side is very thin and it is heavily doped. Okay, so you want more and more carriers, more and more N type. You have more and more phosphorus, right? So more and more phosphorus that can produce lot of electrons for you. Okay, so when the light shines, they must be able to all absorb all the light and then emit a lot of phosphorus. Sometimes, therefore, light from the sun comes in various energy bands, as you know. There is, you all know the VIBGYOR part, right? That is the visible light. But there is also infrared and ultraviolet light. Typically, the thicker the 0.3 micron, right? 300 micron, right? 0.3, right? So the typically the very thin and heavily doped N type, right? That part, has to, absorb as much of the light that is emitted as possible, and then release the corresponding electrons. Now, if that does not happen, if it reflects it off, right? If it is lost in some other way, which leads to heating, etc., right? Or if it is reflected off, that is not useful. Now, when is it reflected off? It's reflected off when it comes at an angle, right? When it is less, right? So typically in some cases, they'll try to keep, if the sun is here, they will try to keep the panel also tilted sometimes. There are all these things that correspondingly tilt the panel as well. Okay, so that it faces direct sunlight. If the panel is little bit not facing the light, then the current that gets generated is much smaller. Okay, so those all factor in, and therefore this side of solar technology is beyond the scope of what we are looking to learn here. But basically, this is the idea. You have a heavily doped N-type, moderately doped but thicker P-type, and then you generate electron hole pairs, and then you end up with a open circuit voltage. So that is as far as the part of the revision from the last class. So now I'm going to introduce a slightly newer but not that much different subject, which is the idea of the transistor. And my hope is I'll get through a little bit of it, and some of it I will continue in the next time. Okay, so now so initially, Shockley invented, the basic ideas in semiconductor, received a Nobel Prize. Later, there was this person called Bardeen. Bardeen was at Bell Labs when he invented this new device called a transistor. Now, a transistor, is there were equivalents of a transistor before. Okay, they had already been invented because World War II produced a lot of inventions, and one of them was this device called a triode. Now, they wanted an equivalent for a triode, which then led to the invention, the transistor. Bardeen also received a Nobel Prize, and the invention of the transistor has changed, our understanding of electronics. Electronics, many people feel, began with the invention of the transistor. And so now the transistor can act as, is used in two forms. Okay, one is it is used as an amplifier in analog electronics, and in digital electronics, the transistor is used as a switch. What do we mean the transistor is used as a switch? What that means is transistor is a three-port device. That means there is a base, it's an NPN device. Previously we had a PN junction, right? A diode had only two ports, a P port and an N port, right? Now there is a third port. Okay, transistor is a three-port device. We had a diode and then we had the triode, right? It mimics the triode. Okay, so it is not a P or an N, not an N or a P, but an NPN or a PNP. So there is a PN and then there is an NP. Okay, so this changes the modality, and there are three terminals on it. One from the N, one from each of the P's, or one from the two N's and the one P, or the two P's and the one N. Okay, so it's a three-port device, firstly, and then it acts as a switch. Now, when used in a certain mode, okay, so when used in a certain mode, it acts as a switch. Now, you might realize that because there are three terminals, you can apply, there are potentially two voltages that you apply. Okay, so there are two voltages that get applied, and then there is there are two currents that get generated. Okay, now how are these two currents related? Okay, in one use case, the transistor, right, acts as an amplifier. In the other use case, transistor acts as a switch. Now, the computer use case is where the transistor acts as a switch. Now, the first transistors that were made were mainly used in analog applications. Okay, it was only much later that they started using them in discrete circuits and eventually in the microprocessor. Okay, now when it was used as an amplifier, right? The first set of devices used in analog electronics were what were called bipolar junction transistors. A bipolar junction transistor has a relationship between the two voltages. One is the base emitter voltage and the voltage on the other side, the collector emitter voltage. Now, those two voltages traditionally there is Vt, and when the VBE exceeds that, then you enter, then you then have a exponential relationship between the two voltages, e to the power of minus VBE by Vt. Okay, so this exponential relationship, right, it means that it is a curve like that. Okay, so then, so now, how do you make it an amplifier? Okay, so that was, that is a whole class in electronics. You can take a full class, which details how those things happen in the context of the BJT. Okay, and you can also understand how it then can be related to the case of the what is called a other devices, which are used in, instead of these bipolar devices, there is also what is called metal oxide semiconductors, CMOS technologies. I will not go into the details of all that, but basically you have an emitter. Previously, you had only a two-port device. Now you have a three-port device. You have an emitter, a base, and a collector. Now, this kind of device, a transistor, is called an NPN transistor. You can also have a PNP transistor, right? So now, an emitter, a base, and a collector. So now, typically, there is a voltage applied between the P and the N, called the or the P and the E. P and the E. So there's a voltage applied between the P and the E, this P and this E, right? So between the base and the emitter. So that voltage is used to push the operating side of the transistor to the part where it is somewhat linear. Okay, and so that when you apply an additional voltage there, then you will have a corresponding increase in the current, which is linear. So it is, what is linear? The increase in the voltage is coupled with an increase in the current that is added. So the deltas, the delta VBE and the delta IC are linearly related. And why are they linearly related? Because you've taken it into that zone. So you have what is you have what you would have learned in Taylor series, right? 1 plus x to the power of n is 1 plus nx plus these other terms which we ignore, right? So when you take it to that linear region, you have this 1 plus nx. So an increment will lead to an increment, right? So an increment this side will lead to an increment that side. So because you have because you're operating at that linear region, so the increment in this will lead to an increment. So that is the basic idea. Now let us now look at the notation here. Okay. Now if a transistor is connected like this, right, this with the arrow out, right, not pointing in, the arrow is pointing out, then it's an NPN transistor. Not pointing in means NPN, right? Not pointing in, NPN means pointing out, right? So this is a out pointing arrow, so that's a NPN transistor. Okay. Now what is a common, right? What is the common? So there is one circuit, one voltage between the base and the emitter, and another voltage between the collector and the emitter. So now you have two voltages that are applied. So this so the emitter is the common terminal between the two voltages, and we say therefore that this circuit, this transistor is connected in a common emitter mode. So how is it operated, right? See, when you have three terminals, base, emitter, collector, right? N, P, N. So base is P. Okay, so this is the common emitter mode of connecting a NPN transistor. Now, what then happens? Then, when like the P is connected to a positive terminal, and the negative terminal is connected to the N, you are in what is called the PN side of it is forward biased, right? PN side is forward biased, and therefore, what does it do? It conducts easily, right? And the other side, on the other hand, whatever whatever increment you apply on this side, you then have a additional small voltage that you apply. That additional voltage gets magnified and is seen on this side. Okay, therefore we say that when it gets magnified, we have another term when something increases, right? So e to the power of vx, right, becomes becomes 1 plus nx, so that n is your magnification, right? And we don't use the word magnification, we use the term amplification in electronics. We say that the NPN device acts as a um, um, acts as a amplifier. Okay, so the important word here is amplifier, not magnifier. We use any increase in the BE voltage will be seen on the other side amplified. Okay, so that is the NPN junction connected as in a circuit. Okay. So now, if two batteries are used for biasing the two junctions, as I said before, one is it is when it is connected in common emitter mode. You can also have the base being the common mode. Okay, so whichever is common to the two circuits. There are two circuits. Yeah, in one circuit you have an increment, produce an amplification as well. Common collector is not like that. Common collector is a very different mode. Okay, now common collector is a stabilizing mode. Now let's not worry about common base and common collector based circuits. Okay, so we will only look at the common emitter mode. Common emitter, the emitter is on the is on the input side and on both sides. If you have a common emitter, the emitter is on both sides, right? The base is only on the input side and the collector is only on the output side. Now, the emitter typically emits a large number of charges in the base region. Most of these are carried over to the thin region and make collector current. Some of the carriers are injected to make the base current. Now, the BJT as an amplifier. The BJT Action Amplifier by raising the strength of a weak signal. So you have a DC bias voltage, IC equal e to the power of minus VB by VT. That's the exponential a curve, right? So and you operate the base emitter is forward biased, right? And therefore forward bias is maintained regardless of the polarity of the signal. So if the signal is an increment on top of the base emitter. So when you increase the signal on this side, on the base emitter side, the collector current correspondingly goes up in a big way. Now the input side, the resistance is kept small. Okay, so now when you have a small change in the input signal, it leads to a big change in the output current. So the emitter current IC caused by the input signal contributes to basically the collector current. So now when that big collector current is what drives the load resistor R, and this results in a large voltage across the load. So let me show you the circuit. So this is this is not the circuit that I am looking for. Okay, this is a common base circuit. Now this is a common emitter circuit. Okay, so here you can see that there is a base emitter voltage which is fixed, that is applied. Now there is a very small resistor added on top, and then there is a base resistor. The base is typically very small. Then you have, now when you add a signal, right, that is an increment on top of the So the VB is also called a bias. Okay, so that is to take the voltage to that linear region. So now in that linear region, see you have this, right? You have VB, right? Goes like that. Now in that linear region, you're taking the transistor to operate in that linear region. So now you apply a signal on top of it, which is a analog signal. It could be, you could think of it as a very small, maybe when I'm speaking, right? So that is converted into a small signal that is produce a small voltage on top of this voltage. Now, the the other side will see a big current which is proportional to this voltage, which is proportional to this incremental voltage. This incremental voltage will produce a larger current on this side, which is linearly proportional to this incremental voltage. Okay, so this larger current is what is produced by across the load resistor RL, and therefore you end up with the total voltage across this load resistor IC being proportional to VC. Okay, so the IC is proportional to incremental VBE, delta VBE proportional to IC. Therefore, that leads to this this big current leads to an amplification across the RL resistor. So across the load resistor, you will see an amplification of the VB voltage. So this is what is is the approximate working of a NPN transistor. Now in a amplifier mode. Now you can also have a PNP transistor which can be connected in a common collector mode. But before that, we have to look at the transistor working as a switch. Okay, so when a transistor is used as a switch, typically a transistor has 4 different modes in which it operates. Right, there is a active region, which is where we were dealing with when we dealt with the transistor as a amplifier. So when you operate it as an amplifier, you work in the active region. Then there is a cutoff region when there is no current, then there is a saturation region when you have a lot of current. Okay, so now this is remember that the other side of the transistor operates in reverse bias. That's why you get that big voltage across it. Okay, so the other side, the second side of the transistor, that is the CE side, it operates partly in reverse bias, right? So because the CE side operates in reverse bias, you therefore have, so if you have a VS signal which is small, the corresponding V across the load will be very big. So that is what amplification is all about. This signal, incremental signal on VBE, produces a faithful amplification. Traditionally, there are also different modes in which transistors are connected. There is what is called a differential amplifier, is 2 BJTs. Then there are also 4 BJTs connected together, which forms another amplifier. Okay, so typically 4 transistors used together is typical for amplification. 2 is a differential amplifier, and then there are other devices also that are made, and analog and electronics is too much to cover in one day, But then we will go back to discuss the transistor as a switch. Okay, and maybe I'll move the working of the transistor as a switch. Now when a transistor is used as a switch, it never operates in the active region, where the amplifier is used. So the transistor is like that. It goes like that and then goes like that. Now it operates either in this zone 0 or in that zone 1. Everything is 0 or 1 in the case of the transistor as a switch. And this whole lot of digital ICs. Look at this computer uses digital ICs. Okay, what is an IC? IC is what is called an integrated circuit. It consists of millions of, and in fact, billion these days, billion, literally, billion transistors in a chip. And this is a whole field that you have to study. You have to do at least a more than a bachelor's degree, master's degree. Once you finish the master's degree, then you will be ready to maybe make a little bit of chips. And if you are lucky, maybe you even do a PhD in the subject, and you come out a doctor of chip making. So I hope some of you do choose that route, and become accomplished in the art of chip design and make all kinds of new chips. There are always so many companies which make so many transistors that power electronics today. And it's a continuously growing field. Okay, so but before I leave this subject, and I will return to it next week to close it out. What I do want to say, in the case of the transistor as a switch, there is, the voltage, that there is an input voltage, right? There are three terminals, right? And therefore, when it acts as a switch, there are multiple types of switches which, which lead to either a current flowing or no current flowing. So under certain circumstances, if the input is a 0, the output may be a 1, or so there are two inputs. Okay, so when there are two inputs, there is the third is the output. Okay, so the transistor, when it acts as a switch, there are because there are three terminals, there are two inputs. Okay, so that is the final idea. I will go into the details of how to make a transistor work in the next class, so that it's much more clearer. Otherwise, I'll just brush through it and you won't understand what's going on here. Okay, but the transistor as an amplifier is basically the current is an increment. When operating the linear region, the incremental voltage is amplified to produce a load voltage which is proportionate to the incremental VBE, and it is much bigger, x times bigger than the increment. That is the amplification level to which the increment happens, right? The multiplier is defined as the amplification, the resultant amplification of the particular amplifier circuit. Okay, then so with that I'm going to stop, but I know some of it is not very clear to you, but because this material requires you to fully understand all the equations involved and all the corresponding nuances of this field, because it's a little more than what we can do in in half hour or 45 minutes. But next class I will come back to transistor as a switch. Maybe we'll look at a couple of problems as well. So with that, I'm going to stop, and then we will meet again next class. Okay, and we will take on a few of the details. Now, before I go, I'm going to quickly introduce to you another topic that we kind of ignored, and that topic is this idea of what is called the photoelectric effect. Okay, now photoelectric effect is related to actually is a idea in modern physics, right? Photoelectric effect was in fact obtained for Einstein the Nobel Prize. So he did not get a Nobel Prize for all the work he did with relativity, but he did get a Nobel Prize for the work he did on the photoelectric effect. So this is the experimental setup. So you have photosensitive plate, then you have electrons, and so in an evacuated glass tube, right? And so the plate C acts as an anode, and the plate D acts as a photosensitive plate. Now you have light coming from a source, right? And that goes through a quartz window and falls on the photosensitive plate. This leads to a current which is set up. Okay, this is the radiation is incident on the plate D through a quartz window. Electrons are ejected out of the plate, and current flows in the circuit. So this is roughly how it works. So we already little bit looked at variety of things associated with this. But I will first start here, and then I will continue with our discussion on transistors in the next class. Just to give some full coverage of this material. Okay. So with that, I'm going to stop, and then we will reconvene in the next class. Now, I'm sorry this material goes very fast, but there is no escaping it. Because there's only so much time you cannot learn everything. Rome wasn't built in a day, but it was built step by step over a long period of time. But for now, just learn this material to the extent that it can be taught in a high school class. So, but what you do need to learn is, the various modes in which these devices operate, and maybe a little bit about some of these circuits, how they are connected, what is an amplifier, what is a switch, how it works, roughly all the details, what is avalanche breakdown, and then how, diode circuits are used, and maybe one or two questions, if possible, involving the transistors as well. So let's look at a few little bit of detail there, and then we will try to wind down all the material in the next class. Okay, so please do get our app and study from it, and get this material together and read the textbooks. They are very, very useful, and we will continue in the next class.